Hi, welcome to Chem with Chem. In this session, we are working paper 2 of CSEC Chemistry from the January 2025 sitting. We're going to just go right into it. This working out is in partial fulfillment of some requests that we've received on the channel for from persons asking us to correct this paper. So we're just going to do it. We're supposed to read our instructions carefully, of course. This paper consists of 6 questions in 2 sections. We're supposed to answer all questions. We're supposed to write our answers in the spaces provided in the booklet. And we know the other instructions. So let us just start. If you're interested in doing sessions, you can call them extra lessons or support session with Chem. Feel free to sign up at chemwithchem@gmail.com. That is chemwithchem@gmail.com. So this is especially for those who are in 4th form and they're going on to do 5th form chemistry next year. Or if you're going to be sitting the subject in 1 year and you need that extra support, Chem with Chem is here for you. All right, so let's just start. All right, so we've changed the format of our work through for this session. We're having some technical difficulties, so we ended up writing the answers before. So section A, we're not supposed to spend more than 30 minutes on question 1. 1A, antacid tablets neutralize stomach acids to produce salt and water. Maxine wanted to investigate the effectiveness of 2 new brands of antacid tablets, Gravico and Gestid. We're to define the term acid here, and an acid is a substance that dissociates or ionizes in water to give H plus ion. All right, so H plus ion is the only positive ion that is produced as a result of that ionization. We're now to define the term normal salt. So a normal salt is a substance formed when all, and the key word here is all the H plus ions of an acid are replaced by the metal or ammonium ion. All right, so we're at part B. The active ingredient in Gravico and Gestid is sodium carbonate. A sample of Gestid was added to dilute hydrochloric acid. And I guess this is really to mimic what happens in the stomach, since the stomach has hydrochloric acid. So we can have an idea of the effectiveness of each of these antacid tablets based on how they react with the dilute hydrochloric acid. And notice here, guys, that they're not giving anyone, Maxine is not testing any of the tablets by ingesting it. There are some assumptions that are made here, like, how the tablets behave with dilute hydrochloric acid is similar with how the tablet would behave were the tablets actually ingested and it were to come in contact with the acidic content of the stomach. Bearing in mind, hydrochloric acid is produced in the stomach. So in cases where we get planning and design experiments, we don't need to get any healthy person and ask them to ingest any tablet. No. That's so when you go to the medical research or when persons are developing drugs and so on. But at this level, we don't ingest anything. We can just look to see what is similar. In this case, the antacid is supposed to treat, find out what condition in the end user we can mimic in the lab and find some way to test it without ingesting it. All right. So the volume of gas produced was measured every 30 seconds for 240 seconds, and the results recorded in table 1 below. The experiment was repeated with Gravico, right? So figure 1 shows the volumes of gas produced in the syringes by Gestid at 4 time intervals. We're to complete table 1 by inserting the volume of gas produced as shown in figure 1. So we're looking at the scale here. on the gas syringe, and we're seeing that from the look of things, each of these lines represent 1 unit. 10 is here. So if 10 is here, it means this is 11, 12, 13, 14, 15, and so on. So this mark that we have right here is 18.5. The second one for 90 seconds is 25.5. The third one at 150 is 37.5. And at 210 seconds is 41. So we'll just fill these in our table and we would get our marks. That would be 4 marks. Now the next thing we're going to do, we're going to use the axes provided on the next page, and we're going to plot the graph for the data obtained from Jested in table 1. The graph of Gravico has already been plotted for you. So we're going to be comparing both graphs to see the effectiveness, which of the 2 antacid tablets is better or is more effective in treating acid stomach. All right, so let's go. Jested is already plotted, and I already plotted Gravico in red. So let us see what we have. All right, so we're going to look at how we arrive at this plot. So we're going to have the values at the bottom left-hand corner. So we're just gonna look at how we plot. So on the x-axis, we're seeing that each of these little, we don't have to focus too much on the scale on the x-axis because we're only plotting 0, 30, 60, 90, 120. So on the y-axis, we have to be a little more careful. We're seeing that 1 cm is being used to represent 2.5 cm cube. So each of the tiny boxes, each of these little boxes that we're seeing right here, each of them is being used to represent 0.5 cm cube. So we have to bear that in mind. So let's go with the first one. So this is where the origin is. We're gonna plot 0, 0. We're gonna also plot, let's see, at 30 seconds, we're gonna plot 10. So this is our 30 line, and 10 goes right here. So we'll plot there. At 60 seconds, we're plotting 18.5. So we're finding our 60 line. We're coming all the way up. 18.5. This is 16, 17, 16, 17, 18. So this right here is 18.5. So we'll come across and we'll put our X right there. At 90, we're plotting 25.5. So we'll come up in our 90 line, and 25.5 would come across here. And we'll put our point there. At 120, this is our 120 line. We're gonna plot 32.5. 32.5 is right here. So that would be our plot. And we'll continue. We have 150, and 150 is here. So this is our 150 line, and we're gonna plot at 150, 37.5. So that's our point there. At 180, this is our 180 line. We're gonna plot there 40. 40 is the thick one right here, so it comes right across. Put our point at 210, 41. So this is our 41 line coming across, and 210 is here. So we plot right there, and 240, we're still producing 41. No increase since the last one. So there's some leveling off, there's some peaking off. So it means that our antacid has run out. It just means that we don't have any further gas being produced. So at 240, we have the same volume. 41, we know where the 41 line is, so we just plot our point right there. Then we draw our smooth curve through all the points, and we get that. So just from what we have here, we can determine which of the 2 antacid tablets is actually better. We can look to see which one produced more carbon dioxide, because if we look at the balanced chemical equation, we should see that there is a correlation between the amount of the volume of carbon dioxide produced and the sodium carbonate that actually reacts. But let us wait on the question. So here we're to use the graphical graph and decide the volume of gas produced at 135 seconds. We're to use dotted lines on our graph to show how we obtain this value. So the value we got here was 40.5. So using the graphical graph at 135, so we'll find 135 on the x-axis and we'll draw a line, broken lines coming up. So we draw broken lines with our ruler and see where it cuts the graphical graph. It cuts it right here. So we draw broken lines coming across and we read off. This is 40.5. All right, the next thing, using your answer in B3 above, calculate the number of moles of gas produced at RTP. And they did not give us RTP. They normally give us what RTP is, right? So we're to do that for the graphical reaction at 135 seconds. So the value we're using is 40.5 cm cube. At RTP, 1 mole of a gas occupies 24,000 cm cube per mole. So what we're doing here, we're taking the given volume and we're dividing it by the molar volume. So it's 40.5 cm cube divided by 24,000 cm cube per mole. Our cm cube will cancel out each other and we'll be left with per mole, which when we take it up to the numerator will become moles. So this is our answer, 0.0017 moles, or in standard form, 1.7 times 10 to the minus 3. Next, they asked us to do a balanced equation with state symbols for the reaction between hydrochloric acid and sodium carbonate. So the tablet would be in the solid state. So here we would change this and would make this solid, since it's the solid state that the tablet would be in. So we're gonna put that as a solid. We have to have the right formula before we balance. So Na2CO3, Na is Na plus, CO3 is 2 minus. One can never catch up 2, but they meet at the common ground. 2, 1 into 2, 2, 2 into 2, 1. So we'll need 2 of the sodium, Na2CO3. HCl, we know that. NaCl, we know it. CO2, it's a carbonate and an acid, so we get CO2 and we get water. Balancing, we have 2 sodium here in the sodium carbonate, so we need to put a 2 in front of the sodium chloride. Putting a 2 there means it's 2 chloride as well, so we need to put a 2 in front of our HCl to get the chlorine balance. And then the 2 HCl checks with the H2O over that side. The carbonate broke down to give CO2 and one of the oxygen going to the water. So those are balanced as well. All right, so we're to determine the number of moles of sodium carbonate that reacted at 135 seconds for the graphical reaction. Now, we know at 135 seconds that 0.0017 moles of the CO2 was produced. So we need to look to see the mole ratio between the CO2 and the sodium carbonate. And when we check that out, we should see that it's in front of the CO2 is well, no number is there, so it means the coefficient is 1. Just like in math, when it's x, when it's 1x, we don't say 1x, we just say x. So the coefficient there is 1. So the mole ratio is 1, is a 1-to-1 mole ratio. So basically, what this means, it means that the same number of moles of carbon dioxide that's produced at 135 seconds, which is our 0.0017 moles, it's the same number of moles of the sodium carbonate that is produced, because they react in a 1-to-1 mole ratio. So once we state that, we will get our marks. And we move on to the next part of the question. So using our answer in B4, we're to calculate the mass of sodium carbonate that reacted at 135 seconds. We already know that the number of moles of sodium carbonate is 0.017 moles. So what we want to do here is to convert from moles to mass, and we do that by multiplying by the molar mass. So what we need to show them is that we know how to calculate the molar mass of sodium carbonate. So it's Na2, so it's 2 times 23, that will give us 46. We have 1 times 12, that's 12. And we have 3 times 16, which is 48. 8 plus 2, 10 plus 6, 16. 6 carry 1, 5. 4 plus 1, 5. 6, 4, 10, 106. That's the RFM. We express that in grams per mole to get the molar mass, and we'd get 106 grams per mole. Multiply that by the number of moles, we end up
0.180 grams.
Per mole cancels out mole, and we're left with our units in grams. So they ask us now, from the graphs obtained in investigation, Maxine suggested that gestid is the stronger antacid, meaning it's the better one. All right, so for this one, we have to look back at the graphs. All right, let us look at the graphs to see what really happened. How much carbon dioxide was produced at the end of the day. For Gravico, we have 40 something, like 48 cm cube of CO2 that was produced, and for gestid we had 41 that was produced. The final volume produced for gestid was 41. There is it leveling off at 41, and for Gravico it was 40. What's that? That's 45, 46, 47. It's 48. So it's 48 cm cube versus 41 cm cube. So we find that Gravico produced a higher volume of CO2, and we know that there's a direct correlation between the CO2 that's produced and the sodium carbonate that reacts. So if more CO2 was produced, it means that more sodium carbonate was actually present in that antacid.
The more CO2 that was produced, the more acid that was
neutralized by the antacid. So it's the antacid neutralizing the stomach acid. So the one that produces more carbon dioxide tells us that that was the one that actually had a higher relative amount of sodium carbonate in the antacid itself. And we're assuming that in this case, she would have to use the same mass of each tablet. Should have to keep that variable constant. Should have to keep the volume of the acid and the concentration of the acid constant. So the one that gives her the higher volume would be the one that had more sodium carbonate present. So we'd have to disagree with Maxine, because Gravico actually liberated 48 cm cube of CO2, while gestid liberated only 41 cm cube, proving that more H plus ions were reacting with Gravico than gestid. In other words, Gravico mopped up or neutralized more acid than the gestid. So again, Gravico won. Gravico liberated more carbon dioxide, which tells us that more of the antacid was present, more of the sodium carbonate was present in the Gravico antacid than in gestid. So we're saying then that Gravico is the stronger one. Stronger is kind of misleading here. It would be stronger here is being used interchangeably with efficient, the more efficient one, the one that mopped up or neutralized more stomach acid. So Gravico won. We will leave it there, and that would give us our full marks. Question 2. Students were asked to observe strips of yam placed in a container of distilled water. After 20 minutes, one student suggested that osmosis was occurring in this yam strip. We're to define osmosis, and it's 3 marks. So there are some key terms that we have to point out. It's the movement of water molecules from an area of high concentration to an area of low concentration. You could say through or across a selectively permeable membrane until there is even distribution. State what the students would have observed after 20 minutes. After 20 minutes, we expect the strips of yam to appear turgid. All right. Some people say they look fat, but turgid is the word. Outline how osmosis supports the particulate theory of matter. So we have to know what the particulate theory of matter states. It states that matter is composed of tiny particles, and that are always moving. So since in osmosis water molecules traverse a selectively permeable membrane, it supports the particulate theory of matter, which states that matter is made up of tiny moving particles. All right. And then for this part, the yam strip, which was a solid, was placed into distilled water, that is a liquid. State how the arrangement of particles in liquid differs from that in a solid. So in a liquid, the particles are randomly arranged and are close to each other, but in a solid, particles are tightly packed in a regular arrangement with very little space between them. That will give us our, we're to account for the observation that the bottles of cold beverages sold at the school canteen often develop drops of water on the sides of the bottles when left to stand. Sometimes we say that it's sweating, but it's not really sweating. The surface of the bottle, the beverage bottle, it's cold. So when air comes in contact with it, the vapor, the water vapor that's in the air, cools and condenses and forms droplets of water that we now see running down on the side of the bottle. So the water we see on the side of the bottle is not the water that's inside the bottle coming out. It's just a cool surface that is present that is causing condensation of atmospheric water vapor. It's similar to if we were to blow on a piece of on a mirror. The mirror is cool and it's actually colder than our breath, and in our breath there is water vapor. So the vapor from the breath would actually condense on the surface of the mirror, which is colder, and so it becomes foggy. So that's water vapor there. So it's same principle. Part C, Table 2 contains information related to the atomic structure of 3 atoms of the elements X, Y, and Z. We're to complete Table 2 below by inserting the missing information for the atomic structure of each of the atoms of the element shown. All right, X, neutron number is given, atomic number is given. The sum of the protons and the neutrons give us the mass number. If we know the atomic number is also the number of protons. So atomic number is the proton number. And we have the neutron number. So protons plus neutrons will give us the mass number. In Y, we're given mass. We're given Y. We're given the mass number for Y. And we're given the atomic number, or the proton number. So if we subtract, if we set 18 from 39, the answer should be our number of protons. All right, so 21 plus 18 will give us back our 39. And then here, we're given the number of neutrons and we're given the mass number. We just need to find the difference between those two. 25 minus 13 should give us back 12. And we should be seeing that, hey, X and Z, that should be jumping out at you. They both have the same atomic number, or the same number of protons. So it means that these two would be our isotopes. Atoms, the same element with the same atomic number, but different number of neutrons. So that will be our isotopes. And then they want us to identify the element that is a non-metal. So if we look, we have 12 versus 18. 12 would be electronic configuration 2, that's in group 2. And 18 would be 2, 8. 8, that would be in group 0. So we know that Y would be our non-metal. And just like that, 15 marks from question number 2. So we're at question 3, and one thing we can be sure about is that we're getting 2 organic questions on our paper 2. Until they change the structure of the paper, that's how it will be. So they want 2 natural sources of hydrocarbons. We can give them crude oil, we can give them natural gas, and if we don't remember any one of these 2, we could also add peat, P-E-A-T. But these are our 2 answers. All right, so they give us the fraction here. They say in B, fractional distillation of crude oil produces several fractions that can contain a range of compounds with varying number of carbon atoms. 3 of these fractions labeled 1, 2, and 3 are shown in table 3. They want us to name one of the numbered fractions. I would stick with the first one. That's the easiest one, refinery gas. And then, you know, if we didn't know that one, we could name fraction 2. Fraction 2, the fraction that they gave there, fraction 2, it's not necessarily right after C4 here, but they just gave us 3 fractions. They're not necessarily in order, in the order that they would actually come off in the fractionating column. If you look at my little sketch of the fractionating column, you're seeing C1 to C4 at the top here. Okay, let's get that. C1 to C4 at the top, then C5 to C12, which would be petrol or gasoline. All right. Naphtha, it would fall a little below. Naphtha would be like C5 to around C9, C10, somewhere thereabout, but you won't always see naphtha being represented. Then you'd have 12 to 18, which would be kerosene, 18 to 25, which would be diesel, and then around 20 to 34, 20 to the 40 region would be lubricating oils and waxes. So the fractions here are not necessarily in order because there is a gap between C4 and C12 that's not represented here. So we have to be careful. All right, but either way, it's just we just need to identify one of them. So fraction 1 is refinery gas, fraction 2 would be kerosene, fraction 3 would be lubricating oils and waxes. And they ask us for one use of fraction 3. To know the use of fraction 3 means we'd have to know exactly what fraction 3 is representing. So let us look at what this looks like, something a little more official. So all right, so if we look here, we should see what we mentioned earlier. C1 to C4, it's called gases here, but they are the refinery gases that we're referring to. Then C5 to about 9 would be naphtha. But then C5 to 10, 12-ish, that would be petrol. Then comes kerosene. Then after kerosene, we'll have diesel. This says C14 to C20. And then after diesel, C20 to about C50 would be lubricating oils, which is consistent with what we mentioned just now. So that would give us the mark. One use of fraction 3, it can be used for fuel, for factory boilers and ships, or as lubricants, or as polishing waxes or solvents for ointments and rubs. All right, and we move on to the next part of our question here, which is asking us, they're saying compound W, part C. Compound W shown in figure 3 has the characteristic odor. They shouldn't say odor. Odor denotes something that smells bad. The characteristic fragrance, that would be a better word right here. The characteristic fragrance of pears and is used in fragrances, exactly, and as a food additive. We don't use, anyway, they want us to circle the functional group. The functional group here, the ester linkage jumps out at me. I don't know if it jumps out at you. It should jump out at you. So the homologous series here is an ester. And before we go any further, we're highlighting the alcohol portion. We highlighted it, anticipating the other part of the question. So we have an alcohol made of 3 carbons, and we have an acid made of 2 carbons on the left side. All right, so characteristics of members of a homologous series, they want 3, same general formula, same functional group, and hence similar chemical properties. That could be split into 2 right here. And then we have the same name ending. All right, and then we'll go over to the other side. We remember what our ester looks like. We can look at it. This is 3 carbons for the alcohol, so it's propyl ethanoate. So let's see what it is that they want us to do. They want the fully displayed structural formula of the 2 molecules that are produced when compound Y is hydrolyzed by dilute hydrochloric acid. So we're going to go back around here. Whenever we have hydrolysis of an ester, we cut right after the carbon-carbon double bond. In the acid, that's where we cut. And when we cut, we're going to put on back OH. We're going to split water and we put OH back onto the acid portion. So we'll be putting OH right here. And then we'll be putting H back there for the alcohol. So that would give us the acid with 2 carbon atoms. That is ethanoic acid is molecule 1 and propanol is molecule 2. We don't want to give away any of our marks. So we just want to ensure that we don't get carried away. Ensure that we don't get carried away, that we just have our answers where they're supposed to go. So we're encouraged to calm down. Even when we think we know it, we calm down and read carefully so we don't make, those simple mistakes and give away marks. So just like that, we would get another 15 marks. So we move on to question 4. This is from periodicity, periodic table and periodicity. Figure 4 represents an outline of a portion of the periodic table. The position of 5 unknown elements L, M, R, Q, and T are shown. L, M is there as well. Not sure if they're going to make mention of M. All right, L, M, Q is here over in that group, 7. T is there as well. Good. They want us to state the name of the horizontal rows and vertical columns in the periodic table. So the rows are called periods and the columns are called groups. They want us to outline 2 factors used in arranging the elements in the periodic table. For 4 marks, we cannot just list the factor. They did not say state or list. So for outline, we would have to give a little explanation, a little supporting information. So atomic number, elements are arranged in the periodic table based on increasing atomic number. Hydrogen 1, helium 2, lithium 3, beryllium 4, boron 5, carbon 6, etc. And then we have based on their chemical properties. Elements with similar chemical properties are placed in the same group. So those that react by giving away 2 electrons, they are placed in group 2. So we can just leave that, and that would be 6 of our 15 marks so far. And we go over. Based on the position of element L in the periodic table, state whether it would react more vigorously or less vigorously with dilute hydrochloric acid than element R. L and R. Let's look. L and R. L is above R, and we know in group 2 reactivity, it's the metals. Group 2, the alkaline earth metals. Metals in general for group 2 specifically, and group 1, but we're focusing on group 2. The reactivity increases going down the group. As the atomic radius increases, then we find that those valence electrons are further and further away from the nucleus. So they're less tightly held, or they're more loosely held. So it's easier for them to be lost. They experience shielding from the inner shell electrons. So it's easier for R to react. R would react more vigorously. So how do we say that? We tell them L would react less vigorously with dilute HCl than R, and the reason, reactivity of the elements increases down group 2 as atomic radius increases, and R is lower in group 2 than L. Then they want us to do a balanced chemical equation for the reaction between element L and hydrochloric acid. So we treat L just like any other group 2 element, just like we would magnesium or calcium. So we treat it like something having 2 electrons in its outer shell that would react and form ions with a 2+ charge. All right, so when we put that with something like chloride, we know that we would need 2 of the chloride to actually go with it, right? 2 of the chloride to go with it. So 1 of this, 2 of that. So it's HCl and L to give L chloride. That's LCl2, which is aqueous, and H2 gas. So we put a 2 in front of the HCl to ensure that we balance the chlorides and the H. So that's that. State 1 reaction other than with hydrochloric acid that is typical of element L. Now element L, and let's look back at where element L is. Element L, based on its position, it would be in the place of where we would put magnesium, but they did not ask us to decode anything. So we could say reaction with air. Reaction with air. That's what we're going to use. Reaction with air is a typical reaction of L. All right, and would expect L to not react with cold water, to react very slowly with cold water, but react with hot water or steam. All right, and then part 5 says an oxide of element L is dissolved in water, which is unlikely because we know all oxides are insoluble except those of sodium, ammonium, and potassium. But we see what they're trying to get at here. They want us to state the pH range of the solution form. There's a pH range, so we don't have to say any one pH. They want a range, so we will go with a pH range of 8 to 14. All right, those are called the alkaline earth metals. So we know anything above 7 is alkaline. So that would give us our mark. Some elements can exist in the solid, liquid, or gaseous state at room temperature and pressure based on their position in the periodic table. Predict the physical state of element T at room temperature. So we'd go back and look at where element T is. Bromine is above element T, and bromine is a liquid. So whatever falls below bromine, we'd expect it to be a solid. Based on the position of element R is in group 2, so it would have a 2 plus charge. I want the formula of its hydrogen carbonate. Now, hydrogen carbonate has a charge of 1 minus, and if that's going with something that's in group 2, like R, we would need 2 of our hydrogen carbonate to go with that. So because it's a polyatomic ion or a radical, we put a bracket around it and we put a subscript 2 to say it's 2 of them going with it. So the formula would be R bracket HCO3 bracket 2, and that would give us 15 marks. So we're at number 5. Again, organic chemistry. We're sure that we're going to get 2 organic chemistry questions. So the condensed formulae of 2 organic compounds A and B are shown below. All right, so they condense it. When it's condensed, we won't necessarily see any functional groups. We probably will have to sketch them, draw them out like I have done here to kind of have an idea of what is at play. So we have a CH3. Let us look. We have a CH3, identified here, CH2, that's it right there. Then a CH, and then we have another CH. So if we have 2 CHs like that connected, they would have to be connected by a carbon-carbon double bond right here. And then we have a CH3, which is at the end. So we can see that this is an alkene. And, without even reading the question, I'm tempted to do the same thing for the next one. So they want the homologous series to which compound A. Well, compound A and B belong. So it's a similar case for compound B. I've seen 2 alkenes being mentioned in the same question. So CH3, CH3. There's a CH2, first CH2. Second CH2, yep. Then there's a CH, the first one, and there's a second CH. So we know that there's a carbon-carbon double bond right there where they have the CH and the CH. There is your unsaturation. It doesn't have the maximum number of the maximum number of hydrogens that can hold on the carbon. And then there's a CH3 at the end. So they both belong to the homologous series called the alkenes. The name of compound A, pentene is fine. It is pentene. If you say pentene to be a little more specific to say where the carbon-carbon double bond is, then all the better. But 1 mark, pentene will work. And then they want the fully displayed structure of compound B. So we're going to just draw it like we've outlined it. There's a CH3, so we spread it out, and carbon must always be taking part in 4 bonds, never 5. 4 bonds. It's tetravalent. So CH3, CH2, then another CH2, then CH, and another CH, then CH3. So that is that. 2 marks for that. And then they want the name of compound B. If we look back at compound B, we'll realize it has 6 carbons. So there's a straight chain there with 6 carbons. 6 carbons. 1, 2, 3, 4, 5, 6. I counted from the right, because when we count from the right, then we see that the carbon-carbon double bond is at carbon 2. Carbon number 2 versus we counted from the left with 1, 2, 3 would be at carbon 4, and would want to name by giving the lowest number possible or the lower number. Not that naming comes up here, but yeah, that's compound B, and they ask us for the name. So it's hexene. We would get away with hexene. If we put hex 2 in, that's fine to give the location of the carbon-carbon double bond. That's even better. But we would get the mark for saying hexene. Compound A displays structural isomerism, and one of its isomers is 2-methyl but-2-ene. 2-methyl but-2-ene. All right, we're going to come to that in a little while. Define the term structural isomers. This is organic compounds that have the same molecular formula but different arrangement of the atoms in space. That's all we need for that. They want us to draw the fully displayed structure of the isomer, 2-methyl but-2-ene. So but-2-ene is the longest chain. But is 4, and the 2 there is telling us that the carbon-carbon double bond is on carbon 2. So whichever side we count from, it will be at, will it be at 2? Well, if we count from the left side, then we get it at 2 for sure. Yes, so this is 1, 2. So on carbon 2, the carbon-carbon double bond is there in the longest chain, but the methyl group is also on carbon 2. So this is our methyl group that we've put on there. And we ensure that all our carbons are taking part in 4 bonds. So this is 2-methyl to say on carbon 2. On carbon 2, there's a methyl group. Also at carbon 2 is the carbon-carbon double bond, hence but-2-ene. All right, so that is that. 2 more marks. So we're just racking them up. Part C, figure 5 shows the structural formula of 2 typical starting materials, compound C and compound D, used for making polymers. All right, this has 2 carboxylic acid groups. That's a diacid, it appears, and this has 2 OH groups. That's a dialcohol. Polymer, it's a macromolecule formed from the joining of many monomer units, at least 50. The functional groups of compound C is the carboxylic group, C, that's bond COOH, and then the hydroxyl group OH from compound D. One use of each of the following polymers: nylon can be used to make fishing line, also used to make fabric. Polypropylene we used to make plastic buckets. And just like that, 15 more marks. How many minutes did that take us? All right. What do you prefer, organic or inorganic? Put it in the comments under this video. All right, so part 6. Nitrogen is used in the manufacture of ammonia gas. 2 physical properties of nitrogen: colorless, odorless. Don't know if we could split that into 2. It's insoluble in water, and it has a similar density as air. That's nitrogen. Don't mix that up with ammonia. Properties of nitrogen. So it's a nitrogen that that's been referenced here. Okay, they want a label diagram to show the apparatus used for the laboratory preparation of ammonia. It doesn't have to be this one with the U-tube, right? It doesn't have to be this one. There's another one where the drying agent is at the base and the gas goes up. But this one is popular. This one would work. We'd need to have our heat source, ensure that the system is sealed from that, or the gas produced would be traveling across here. It goes down here where it's dried, and then it goes up, and we said that that is the upward delivery. Ammonia is less dense than air, so it would go up and displace the air downwards. And then Yeah, that's that. But that's what we need to give them for the 3 marks. And then over here now, they're saying write a balanced chemical equation for the reaction that takes place in the laboratory preparation of ammonia. We can use calcium hydroxide, that's a base. So a base and an ammonium salt will give us salt, water, and ammonia. All right, so let's see. The chloride here, in calcium chloride, it's CaCl2, so we need to put a 2 in front of our ammonium chloride to balance that. When we do that, we automatically have 2 nitrogen, which does not come out of the ammonia fully. It doesn't break down fully. So we'll put a 2 in front of the ammonia to fix that. That makes us now have 2, 3, 6 hydrogen. Let's see. Oh, I think this needs another 2. That would give us 2. Let's see, 2, 3, 6 hydrogen there, plus 2, making 8. On the left, we'd have 2 4s, 8, plus 2 here in the calcium hydroxide. So we'd also need a 2 in front of the water to ensure that everything is fully balanced. So that is it. Everything is balanced now. Explain why concentrated sulfuric acid, a typical drying agent, cannot be used in the preparation of ammonia gas. All right, so ammonia is basic, the only alkaline gas there is, and concentrated sulfuric acid, as the name suggests, is an acid. So if we were to use concentrated sulfuric acid to dry the ammonia, it would actually react with the ammonia. We don't want that. So we could use calcium oxide, which is a drying agent that would not react with our ammonia. So that would be the preferred drying agent right there. And the laboratory test for ammonia is with moist red litmus, and it would turn the moist red litmus to blue. We could also dip a glass rod in concentrated hydrochloric acid and put that in the presence of the gas that we're testing to see if it's ammonia. And if we get dense white fumes being formed, then we'd know that ammonia is present because it reacts with HCl to form ammonium chloride. And then for our last 3 marks, to give us the 15 and full marks, they're saying here ammonia is used as raw material in the manufacture of fertilizers such as ammonium nitrate. The excessive use of fertilizers may lead to harmful levels of nitrates in the environment. List 3 harmful effects of excessive nitrates in the environment. We could have pollution of groundwater, and we could have eutrophication, but we don't just leave it at eutrophication, because eutrophication can result in other harmful effects. All right, so from eutrophication, where we get the overgrowth of the algae, which now blocks out sunlight from the plants that are beneath it, resulting in them dying. When they die now, we know that bacteria break them down rather, using up oxygen. And then when this oxygen is used up, we have what we call dead zones, where you won't have any aquatic life resulting as a result of that. So it's pollution of groundwater, eutrophication, and then from eutrophication, we also have the creation of dead zones. So this is it. This is it. We've come to the end of this session. How did you fare? How did you find this paper in general? All right, just remember, if you find value here, just share it with a friend. All right, it's too good to not share. And if you're interested in doing support classes, or if you want to call it extra lessons, or whatever you want to call it, for Form 5 chemistry, 5th form chemistry, you can sign up, or you can register by sending an email to chemwithchem@gmail.com. Right? Thank you for making it Chem with Chem. As we always say when we're leaving, we say copper later. Have fun with the chemistry. All the best in your exam, guys.